Assalamualaikum warahmatullahi wabarakatuh and a very good day to all. So today we're going to look at a new topic under the mechanics of machines, and we're still talking about the power transmission system. So last lecture we have looked at the power transmission system, which utilize a belt as the means of the power transmission. So today we're going to look at another power transmission system, and we're going to look at a gear drive. Yeah. Okay, as introductions, gear can be described as a tooth wheel that when meshed with another tooth wheel, or sometimes they call it pinion, will transmit rotation. So basically, the means of the transfer of power in the gear system is through meshing of one gear with another gear. Right? So if you remember when we talk about the belt system, the means of power transfer is basically by the means of the power is being transferred in the belt gear system by means of the belt itself, right? So you have a mesh of pulley to the belt, and then the belt will mesh another pulley. So that's how you transfer power in belt system. But in the gear system, then basically you have two tooth wheel close to each others, and the power is being transmitted by means of the meshed of the tooth of the two gear system. Right? Um, so the primary functions of the gear is to transfer power. And, that's we know that, and from one shaft to another while maintaining definite ratio between the velocity. So this is one advantage of gear system. So if you remember when we talk about uh, belt system, so the two pulley connected by belt, right? So the velocity between the input and the output, they say this is in, this is out. Input and output depends on few things. One is depends on if there is a slip between the pulley and the belt, right? So if there's slip, then it will affect the velocity between the input and the output. Or if the belt is elastic, if the belt is elastic, then also you'll have it will affect the velocity of the output or driven pulley, right? But in the gear transmission system, then you have definite ratio between the velocity of the input and output shaft rotation, right? So the teeth of the driving gear mesh push on the driven gear teeth, exerting force component perpendicular to the radius gear. Thus, torque is transmitted, and because the gear is rotating, power is transferred. So in the gear system, so I'm going to, the simplified drawing of the gear system is just two circles. We're going to talk more about that, what this circle means later on. So this is the radius, so of the two gear system, and basically the mesh point is at the center there, and the power is being transmitted perpendicular to the radius of the gear system, of the gear itself. So that's what it says here. Power is transmitted exiting a force component perpendicular to the gear radius, and then torque is transmitted because the gear is rotating. The power is transmitted. So in terms of rotations, if this gear is rotating clockwise, and this gear will rotate counter clockwise, and gear are good transmitters that than chain drive or belt drive. So I mentioned just now in the gear system, it's a very good torque transmission system compared to chain or belt drive. because of the slip, because of the slip between the belt and the pulley. Then basically you are limited to how much torque you can transfer. If the torque is too much, then you have a slip between the belt and the pulley. In the gear system, if the torque is just too much, then it will just stall or it will break, right? So that's also the disadvantage about the maybe the gear system. In the belt system, if too much torque, then you have slip between the belt and the pulley, so you won't damage the pulley itself, right? Gear are standardized as to tooth shape and size. So whenever you design a gear, don't create your own tooth shape of a gear system or the size. It should be standardized. So you can open up a handbook on gear, and you can find various shape of gear system and size of gear system. So you just follow what's being standardized. There are many types of gears out there, but we're going to look at three types of gear that's commonly used. The first one is called parallel axis gear. So examples of parallel axis gear is spur and helical gear system. Uh, then you have non-parallel coplanar gear. So the naming convention is looking at the axis of the two gear systems that's meshed together, right? So the second type of gear is non-parallel coplanar gear. So it indicates that the gear are not parallel. The gear shaft is not parallel to each other, but it's the same plane. So some examples of it is a bevel and spiral gear system, right? And the other gear system is called non-parallel, non-coplanar gears, and examples is worm gears. And we're going to look at in detail uh, uh, each of the gear system that we mentioned in here. So let's look at the parallel axis gears. So this is the first type of gear, and this is the simplest and the most popular type of gear that's being used out there. Uh, they connect parallel shaft and can transfer large amount of power with high efficiency. Example is a spur and helical gear are two of the primary gears in this particular category. So if you look at these two gear system, so if you draw a shaft of the two gear system, so this is a shaft of the two gear system will be at the center, or if it's from here will be at the center, right? So basically the two gear shaft will be parallel to each other. That's why it says that is a parallel axis gear system. The helical gear teeth are cut with an angle. Helical teeth enter the meshing zone progressively and therefore have a smoother action than spur gear teeth. So helical gear also tend to be quieter. So if you look at these two gears between a spur gear and also helical gear, the difference is basically on the way the tooth are being cut, right? The tooth over here is being cut straight, right? And on the helical gear is cut at the angle. So the reason why it's being cut at the angle is this. So if it's cut at the angle, such as helical gear, so it will enter the meshing zone progressively. So rather than and so when this spur gear rotates, right? So the meshing between this gear and the driver and the driven gear will happen in a line, right? Because you have a straight cut, so you have one line and you need to align with another line, right? But in the helical gear system, since it's is a cut at an angle, so during meshing between the driver and the driven gear, so the meshing is being done progressively. so bit by bit rather than at one go, because of a straight line. So because of the slanted angle, then basically it will enter each other at almost point to point rather than line to line. So that's why it says that it will have a smoother action than spur gear, and it tends to be quieter. So these are the two advantage comparing helical gear and spur gear. And helical gear can also transmit heavier load and have a longer lifespan compared to the spur gear. So helical gear can transmit heavier load and have a longer gear life when compared to spur gear. Because of what? Because basically, since it mesh to each other's gear system progressively, and it's quiet, so you can just imagine the friction, so on and so forth, will be much less on helical gear compared to the spur gear. So that's why it can transmit heavier load and have a longer gear life compared to spur gear. But the disadvantage is basically helical gear is more costly to make, so it'll be more pricey compared to the spur gear. The other gear system is non-parallel coplanar gear, and the examples of this particular gear system is bevel gear. So if you look at this particular gear arrangement, so you can see that the reason why it's called non-parallel coplanar gear, because the axis of the shaft of the gear is not parallel to each other, right? So the shaft is not parallel to each other, but the plane where the center of the shaft is in the same plane, so is in the same plane, right? So the center of the shaft will be in the same plane, but they are not parallel to each other. So that's why this particular gear system is called non-parallel coplanar gears. And the main functions of a bevel gear is the redirections of power around a corner. So you can transfer power at a 90 degrees angle in this particular examples. So if this is a driver, so if it is a driver and this is driven, then you can actually see that the power is being transferred at 90-degree angle, right? Example of the application of such a gear system: horizontally mounted engine power is transferred to a vertical mounted rotor shaft on helicopter. So in a helicopter, for example, so they say this is helicopter, doesn't look like a helicopter, but if you have a engine on the top, let's say for example over here, and this engine have a rotational movement, so inside it should be a shaft. Rotational is in this direction, but it transfer its power to spin the road the helicopter blade on the top in this direction. So basically this is the redirections of power at almost 90 degrees. So that's example of the co-parallel coplanar gears and its application. So the third type of gear system is called non-parallel non-coplanar gear. So example of this gear is the worm gear. So shown here is worm gear. So if you can just imagine this, right? So the axis for this particular gear system is not parallel to the axis of the other gear system. So the way this is working is this particular gear will turn in certain direction in that motion, and it will translate the power to the particular to the other gear system but the movement of the gear system is not in rotational but in the in a linear movement. So it transformed the rotational movement to linear movement for worm gear. So the non-parallel, non-coplanar gears are more complex in both geometry and manufacturing than the previous gear type because of the nature of the gear system. So you are translating the rotational movement to the linear movement. So again, if you look at this, the shaft is not parallel, and the center of the shaft is also not in the same plane. So because of that, this is called non-parallel and non-coplanar. So a worm gear drive with cylindrical teeth illustrate this class of gear system. The axes are non-parallel and non-coplanar, and it provides higher reduction ratio than coplanar or simple cross-axis gear sets, but their carrying load capacity is low. So one of the characteristic of this particular gear system is you cannot apply too much load on it, right? So the load carrying capacity is low. The contact pressure is extremely high, and their wear rate also very high. So this is the characteristic of such gear, worm gear. Thus, these gear are used only for light load application. So such a gear system is commonly used in many of our equipment in the lab. So, for example, if you use a CNC manual CNC manual lathe machine, so if you want to move the plate right, left and right. So this is, let's say, for example, this is where you mount the tools, right? This is where you mount the tool, and you want to move it along the x-axis. So the way you move it along the axis is basically there's a wheel for you to rotate it, right? So when you rotate the wheel, and the assembly tool holder assembly will move linearly left to right. So this is one of the common applications of such a gear system. As I mentioned earlier, the gear tooth geometry is standard, has been designed in standard design. The size and also the shape are standard, and there are many gear geometries and also nomenclature to define the gear system. So listed here, there are quite a few nomenclature and geometry of a gear system. So you should take a look at it and try to understand it. It's very important if you want to design the gear system. We are not going to deal a lot on the gear geometry and nomenclature in this particular class, but there are few geometry that's important for our application, which I will cover later on. So for this, please do take a look at it and read it on your own. Okay. As mentioned earlier, the power is being transmitted from gear to the to from driver to a driven gear. Sometimes they call it gear and pinion, by means of meshing of the tooth of the gear system. So so we want to look at the line of action and pressure angle of during the meshing between the driver and driven gear system. So the purpose of meshing uh, so the purpose of meshing gear teeth is to provide constant instantaneous relative motion between the engaging gear system. So when you have two gear teeth meshed together, then basically it provide constant instantaneous relative motion between the engaging gears. So whatever rotation movement from one gear will be translated and transmitted to the other gear system efficiently. To achieve this tooth action, the common of the curves of the two meshing gear tooth must pass through a common point called pitch point on the pitch circle. So basically, the point where the two gear mesh together is known as pitch point. So this is pitch point. And this pitch point is located on the pitch circle. So whenever we draw the two gear system, the simplified gear will look like a circle without tooth on it, right? And we assume that the contact point between the two gear system is called pitch point, right? And this is actually located on the pitch circle, and this is pitch circle. Right? There's a pitch circle and this is pitch point. So you have to remember that when when we talk about a pitch diameter, then this diameter of this particular circle, of this particular circle, and basically we are referring the outline of the gear to represent the gear, and that outline is called pitch circle. Okay. So let's look at some of the methods of calculating characteristics of the gear system. So we need to understand this basic gear theory for that. So whenever we do some analysis on the gear system, usually we put the gear in a box, in a black box like such. Right? So inside this, there's a gear system. It can be train gear system. It can be epicyclic gear systems, so on and so forth. So usually we do not draw them, right? But it's inside here. And usually, what you have as input and output of the shaft is the one that actually concern you. So what happened to the input shaft? So for example, one is the input and two is equal to the output. So we are concerned with what happened to the input to the system and the effect of the gear system inside the box to the output shaft of the system. And one of the common performance measures that we used and we calculate for the basic gearbox theory is called gearbox ratio. And gearbox ratio is simply the input speed over the output speed, and the speed can be either in RPM, so N1 and N2, so this is RPM, or it can be in the form of angular velocity. So this is radian per second, the unit. So this is radian per second over radian per second, or it can be RPM over RPM. So both of them is basically known as gearbox ratio. So in the basic gearbox theory, when you talk about power transmitted from the input to the output, basically we can then calculate power is equals to, again, torque times omega, right? So torque this torque is in unit Newton meter, right? Omega is in radian per second. So the unit is actually in Newton meter per second, so this is joule per second, so this is actually watts. So that's why uh, power is equals to torque times angular velocity, uh, and the units is actually in watts. So if we say that for ideal gear system where you don't have any power loss, so efficiency is equals to 100%. There's no power loss due to heat, friction, so on and so forth. Then basically what we can say, if that's the ideal case, in actual case there's some power loss. So assume that's ideal case. So then what we can do, then we can say that T1, so we can say that power power 1 equals to power 2, right? So what's power? Power is equals to torque 1 times omega 1 equals to torque 2 times omega 2. And what is omega? So this is torque 1. Omega is simply 2 pi n1 divided by 60 equals to tau 2. 2 pi omega n2, sorry, n2 divided by 60, right? So basically then I can cancel out all this term, and what we have is tau 1 n1 equals to tau 2 n2. So then I can rephrase this in terms of n1 over n2 equals to tau 2 over tau 1, right? So this term is equals to gear ratio. Gear ratio. So I can define gear ratio as n1 over n2 or torque 2 over torque 1, right? So I have another ways of defining gear ratio now, based on the ideal gear situation, where the efficiency is 100%, is equals to n1 over n2 or tau 1, which is torque at 2 over torque at 1, right? And I can define the efficiency. So I can define the efficiency as this equation, right? So again, if you look at the calculation of power equals to tau times omega. So for power out is tau 2 times omega 2, uh, then divided by tau 1 times omega 1. So if you do the math, then what we get is n2 t2 divided by n1 t1 is equals to efficiency. And usually for real gear system, there is a power loss due to friction. That's why if there's a, let's say for example, your car is running, the transmission is turning. If you put your hand on the transmission box, you can feel heat, though. So that indicates there's power lost due to friction, and that friction turns into heat. So there'll be some inefficiency in the system, and you can calculate the efficiency of the system by using these particular equations. For n1 times t2 or tau 2 divided by n1, n2 times tau 2 divided by n1 times tau 1. So again, n2 is the rotational speed of the shaft, and tau or t is the torque of the shaft. So in designing the gear system, one of the element that you need to be able to calculate is the the gearbox body holding torque. So if you imagine there is a torque applied in the input, there is a torque on the output of the shaft, and basically if nothing holding the body of the gearbox, then this body will also rotate, right? So we need to calculate what is the torque um, uh, that the body of the gear actually experience. So that's, we call it T3 or tau 3. So having knowing how much torque is being applied on the body, then we can actually size up the bolt or the holding mechanism to hold the gearbox in place, right? So um, gearbox body holding torque, the gearbox body has to be clamped or bolted or secured in order to stop assembly from rotating, as I mentioned just now. And a holding torque T3 must be applied to the body such that the summation of torque equals to 0. So you need to be able to do summation of torque, right, equals to 0, equals to T1 plus T2 plus T3. So if you know what is T1 and T2, then you should be able to find what T3 is. If you find T3, then you know what is the holding force needed to secure the gearbox in place while shaft, the input shaft and the output shaft rotating. Let's look at the examples of the gearbox system problem. So for this particular problem, we have is given that the gearbox has an input speed of 1500 revolution per minute clockwise, and the output speed of 300 revolution per minute anti-clockwise. So let's sketch the gearbox system. So again, as mentioned earlier, the gearbox system can be represented by just a box, and you have an input shaft and the output shaft. So I just name them as input, in, and this is out. And we designate the input as 1 and output as 2. So what is given? So it's given that the rotational speed of the input is 1500. So and 1500 revolution per minute, and this is clockwise. So this is clockwise, and the output speed is n2 equals to 300, and this is anti-clockwise. Okay? As also given that the input power P1 equals to 20 kilowatt, 20 times 10 to the power 3 watts, right? And it's given that the efficiency of the system is 70%. So we asked to find the following. One is the gear ratio. So for the gear ratio is simply equals to N1 over N2. And we know what N1 and N2 is. So this is 1500 divided by 300. And this is equals to 5. So the gear ratio is equal to 5. It's quite simple. Second one is the input torque. So we are asked to find input torque, which is tau 1. And basically tau 1 is related to power, right? P1 is related to P1. So, so power P1 is equals to omega tau 1 times omega 1. right? So I can find tau 1 equals to uh, power 1 divided by omega 1. So we don't know what's omega 1, but we can convert omega 1 to n1. So this is equals to p1 divided by, so omega 1 is simply 2 pi n1 divided by 60. Right? And so we know what's a p1 and what's n1, so we can calculate this. So this is equals to p1 is equal to 20 times 10 to the power of 3 watts. So make sure that you convert it from kilowatts to watts, so that we have consistency in unit times 60 divided by 2 pi times n1, and n1 is equals to 1500. And if you calculate this is equals to 127.3 unit is Newton meter. And the directions of the torque, remember torque is rotational force, so the direction of the torque is same as the directions of the shaft. And given that direction of the car shaft is clockwise for the input, so tau 1 would be clockwise also. Next, we asked to find the output power. So output power is power 2 is equals to tau 2 times omega 2, but we don't know what's tau 2, right? So because of that we cannot find power 2. But there's another relationship that we can find tau 2 power 2. So we can calculate efficiency. So efficiency is equals to power out, which is power 2, P2 divided by power in, which is P1. And P1 is given. So P1 is given as 20,000. And the efficiency also given. So I can calculate P2 equals to nu times P2, P1, sorry. And that's equals to 0 0.7, 70%, times P1 is equals to 20 times 10 to the power of 3 Newton meter. So this is sorry. So this is what. So this is equals to, if you calculate this, is equals to 14 kilowatts. 14 times 10 to the power of 3 watts. Right? So this number 3. Right? So next we have to find the output torque. So the output torque is so next is output torque. So output torque is basically tau 2. So if you look at this particular equation, right? So I can calculate the P2 tau 2 if you know P2 and omega 2. So I can use this equation. Tau 2 is equals to power 2 divided by omega 2. We don't know omega, but we know what's n2. So we can convert this equals to P2 divided by 2 pi n2 times 60, right? And basically if you plug in the number, we have P2 is equals to, we calculate P2 just now, P2 is equals to 14 times 10 to the power of 3 times 60 divided by 2 pi, and n2 is equals to 300, right? So if you calculate that, then basically that would be 445.6 Newton meter. And finally, we have to find the holding torque. So I just let me draw a sketch very quickly. So we have the gearbox system. So this is in, so tau in, and this is torque out. And then we assume, so we know that the tau in is clockwise, This is counterclockwise. We assume that the torque on this is clockwise, right? The torque T tau 3 basically this is the torque subjected on the what do you call it, on the body of the gearbox, right? So then we do summation of torque must equals to 0, and we assume that in terms of the direction, in terms of the plus and minuses, we assume that to the right clockwise is positive and counterclockwise is negative, right? So basically I have tau 1, which is plus. So tau 1 is plus. So then this is tau 1 is positive clockwise, right? Plus tau 3, which is also clockwise, so it's positive. And tau 2 is negative because it's counterclockwise, so it's negative tau 2 must equals to 0. So then I can calculate what is the holding torque. Tau 3 is equals to tau 2 minus tau 1, and we have tau 2 is equals to uh, 4 4 5.6 minus and tau 1 is equals to 1 2 7.3, right? And so this is equals to tau 3 is equals to 318.3 Newton meter. So basically this shows that the torque subjected on. So so the tau 3 is 318.3 Newton meter, and since this is positive, then basically it indicates that our assumptions that this is the assumptions that we did, that this tau 3 is clockwise is correct. So if you look at the answer, it's here, it says that anti-clockwise tau 3 is equals to negative 318.3 Newton meter anti-clockwise. So there's a redundancy, so there's a negative and anti-clockwise, so it's actually a clockwise. It's actually clockwise. So let's shift gear a bit and look at the various type of gear system. And the first gear system that we're going to look at is called a simple train gear. So this is examples of the simple train gear, where you have gear connected together at the edge of it in series as shown here. So first, the directions of the rotations is reverse from one gear to another. So you have if you have a, a train gear as uh, in the figure here. So this is gear 1, gear A, gear B, and gear C. Then basically the direction of the rotation is reversed from one gear to another one. So if A is rotating clockwise, then gear B will be counterclockwise, and accordingly gear C will be clockwise, right? And the teeth of the gears must be all the same size, so that as gear A advance one tooth, so does gear B and gear C. So it says that the spacing of the, for example, if we have, this is two gear system that mesh together, right? So the bigger gear will have certain number of tools. So let's say, for example, if I call this one, gear one, this is called gear two. So this is gear two. So the spacing here, this section, and the spacing of the other gear system, this section, must be the same. They must be the same. So that arc and this arc must be the same. So that the gear must be all of the same size, so that as gear A advance one tooth, so does gear B and gear C. So as this gear one advance one tooth, then gear two will also advance one tooth. Okay, so that's the requirement for the simple train gear system to work, for any gear that mesh together to work. And it's stated here that the velocity at any point on the circle must be the same for all gears. So if you take any point on the gear system that's connected together, that are meshed together, any at any given point, the magnitude of the velocity must be the same. So if I take here, then the speed will still be v, and this v is equals to this particular speed, equals to that particular speed, equals to the velocity of this particular point. And if I take even at this particular point, if I find the linear velocity there, this still see b v. So they are all must be the same. Right? So with that, then basically we can say that the velocity at 1a equals to velocity at gear B must equals to velocity at gear C, right? And the way to calculate the velocity is basically equals to omega a times r a must equals to vb can also be defined as omega a times r a and equals to omega c times r c. Right? So this is basically and you can define omega in terms of rotation per minute in terms of rpm. So if you convert that, then this become 2 pi NA RA divided by 60 must equals to 2 pi N. So this is supposed to be B, sorry. So this is B times RB, and this is NB RB divided by 60, and this must equals to 2 pi N CRC divided by 60, right? So I can then simplify this equation by cancelling pi and 60, and what I have is n2r. N2r is equals to dA, so 2 times the radius is equals to diameter. So what I have is NA dA times NB dB equals to NC dC, right? So based on this, then I would like to introduce another constant called module. This module says this. The module is equals to the ratio between d over t. The reason why this is true is this. So if you look at these particular assumptions that we make just now, we are saying that the spacing in between the tooth, right? The pitch of the tooth must be the same for the gears that they are connected together, right? So if I want to calculate that, it's basically if I say that for gear number one, it has a T. Let me erase this. Let me see. Okay, so let's say no, this particular gear one has a T1. T1 is represent number of gear, and it has a radius of a diameter of D1, right? So similarly, I can say that T2, the gear 2 has a T2 has a number of gear tooth. So T refer to number of teeth in the gear system. So it's T2, and it has a diameter of D2. So if I want to find the ratio between if I want to find the space in between the teeth, so this is this arc, right? I can define that as the circumference, which is 2 pi r1 divided by number of teeth t1. Similarly, for the gear 2, I can find the space between the gear, this arc, that's equals to 2 pi r2 divided by t2, right? So if you look at this, then we are saying that this arc for gear 1 must be the same length for the arc in the gear 2, right? So then we can say that these are equal, right? So that I can rewrite this, I can cancel pi. Then I have d1, because 2 times radius 1 is equals to diameter 1 divided by t1 equals to, again, d2 divided by t2, right? And this ratio must be the same for all gears that are connected together, right? And we call this module, right? So this is the module. So the modules can be calculated basically as a ratio between So I mentioned just now, the module can be calculated basically as a ratio of diameter to the number of tooth for individual gear, and this module must be the same for the gears that are meshed together, right? So basically, with this in mind, then basically I can replace this D with a module. So mentioned as I mentioned over here, then modules equals to diameter over t. So basically, then diameter is equals to module times number of tooth. So with that in mind, then I can replace d is actually equals to m t in every part of this particular equation. So this become Na times m t a equals to n b module times t number of tooth of gear b equals to n c times modules times t c, and I can cancel m. So what I have is an a times ta equals to nb times tb equals to nc times tc. So this is how this equation is derived. Okay. Okay, let's look at examples of the simple train system. A simple train system has three gears. Gear A is the input with 50 teeth. Gear C is output 50 teeth, and gear A rotates 1,500 RPM anti-clockwise. So calculate the ratio of the output speed. So let's sketch it first. So we have a three gear system, one, two, and three gear system. So this is A, B, and C. So A is input. So this is input. This is output, right? And it's given that the gear A is the input and has 50 teeth. So TA is equals to 50. And gear B, we don't know what the gear B is. Gear C is output. So C is output, and TC is equals to 150. The gear A is rotates. The gear A rotates and A at 1,500 anti-clockwise. So rotations of A is anti-clockwise. So this is rotation of the input. Calculate the gear ratio and the output speed. So first we need to calculate the gear ratio. So gear ratio is equals to an input, which is A, over n output, which is C, right? We know what is n is, but we don't know what nc is. However, just now we know what t is, right? Number of teeth for a, n, and c. So we know the relationship between n and t just now. Then basically we're saying that the relationship is na times ta equals to nc times tc. So I can calculate an a over nc must equals to tc over ta, and that's equals to tc is equal to 150 and ta is 50. That's equals to 3. So that's the gear ratio, right? Okay, second question is what is the output speed? So basically we know what's the gear ratio just now, right? So gear ratio equals to na over nc equals to 3. We know that, right? So we want to find an nc. Nc is equals to na divided by 3, and na is 1,500 divided by 3. This is equals to 500 rpm. So the rotation of C can be determined from here. So we know that the rotations of the gear system that's meshed together reverse from one to the next. So if this is clockwise, this is counterclockwise. This will be P will be clockwise, and if B is clockwise, then C would be counterclockwise. So and C will be counterclockwise. So the next section of the question says that the input torque on A is 12 Newton meter. So we know that torque A, which is input, is equals to 12 Newton meter, and the efficiency is equal to 75%. So calculate the output power. So we want to find out P output, which is PC. PC. So we can calculate a PC power C is equals to torque at C times omega C. However, we don't know this value. We know omega C. We can calculate that from NC, but we don't know TC, so we cannot do that. So this is unknown. We don't know. So the other way to calculate PC, since we are given the efficiency, then basically efficiency is equals to output power, which is PC, divided by input power, PA. Right? So we can calculate for the PC is equals to nu times PA, and this is simply nu times PA can be calculated based on tau A times omega A. So this is simply equals to tau A times 2 pi NA over 60. And we know all this value. This is 75%, 0.75 times tau A is given is 12 Newton meter. So this is 12 times 2 pi times NA is equals to 1500 divided by 60. So if you calculate this, then basically you get the power output equals to 1413.7 watts. Okay, the last question is we need to calculate the holding torque. So for that, let me draw the gearbox system. So we have the input here, output here. So we know that this is tau A, this is tau C, and tau A is given. We know tau A is equals to 12, and this is counterclockwise. And tau C, if you look at the orientations, is also counterclockwise. Right? But the value of TC we don't know, so we have to figure out what's the value of TC, and we assume that the holding torque is tau H, a clockwise direction. So now we have to find a TC now. So we know that PC, we calculate just now the PC, power output is equals to tau C times omega C. And we can find omega C because we know what's the NC is just now. So we have 500 RPM. So PC, then I can calculate tau C is equals to PC divided by omega C. And this is equals to PC divided by 2 pi and C divided by 60, so it's times 60 on the top. Right? So if I plug in the number, what I got is basically PC is PC is 1413.7 times 60 divided by 2 pi, and C is equals to 500. And if we calculate this, then we got tau C as 27 Newton meter. So we know TC is equals to 27 Newton meter. So I'm just clearing up the page and redraw this gear box system. So we have tau A is equals to 12 counterclockwise. Tau C is counterclockwise is 27 Newton meter, and holding torque we assume is a clockwise direction. So we do summation of torque equals to 0 at static condition, and we assume that the clockwise directions is positive, right? So with that, then basically we have minus tau A because it's counterclockwise, plus tau H minus tau C, right? So TH holding torque is equals to uh, tau A plus tau C, and this is basically equals to 12.27, and this is equals to 39 Newton meter, and the directions of the torque is clockwise because it's positive. So let's look at another gear system called compound gear. So compound gear are chain of simple gear trains with input of the second being the output of first. So examples of compound gear as shown in this particular figure. We have four gears in this particular system. So gear B is the output of gear A and B. So if you look at this, there is one train gear, which is gear A and gear B. So in this system, A is input. So due to this, then B is the output of the gear A and B. And gear B and C are locked to the same shaft. So gear B and C, they are connected together with the same shaft. And gear C, so this is gear, not bear. So this is a gear. Gear C is input of gear C and D. So if you look at another train gear system, C and D, so is C is the input and D is the output. And basically the velocity of each tooth of A and B are the same. So since A and B is a train gear, so at any given point of the gear A and gear B, the velocity is supposed to be the same. So velocity can be calculated as omega, which is angular velocity times t. T is number of tooth. So let's explain this a bit. So if we say that V A is equals to VB, and we know that V is equals to omega R, right? And we have already also look at the constant named modules, and modules is equal to diameter over T, right? and T is number of teeth in the gear system. So basically using this is equals to 2R over T, right? So I can define R to be equals to M T over 2, where M is module. So for any given gear system that are meshed together, module are the same, times T over 2. So if I replace this in here, then what I have is velocity is equals to omega times M T over 2. So with this end, if we say that VB equals VA equals to VB, then basically omega A M TA over 2 is equals to omega B M TB over 2. So we can cancel out 2, and since M module for a gear system that gears that are meshed together, they're the same. So M is cancel out. What I have is omega A is times TA equals to omega B TB. So this is where this equation comes from. Okay. So for the combination C and D gear system, so C and D gear system, then using the same argument, we can say that omega C times omega T, omega C times TC is equals to omega D times TD, right? So based on this, then basically we can rewrite this equation saying that omega A over TB is equals to omega B over TA, and we can also say that omega C over TD is equals to omega D over TC. Then we can actually solve the omega A equals to TB omega B over TA and omega C TD omega D over TC. So if we say that if we multiply omega A and omega C, so omega A times omega C, and that's basically equals to TB omega B over TA times TD omega D divided by TC. Right? And if we simplify this, then basically if we rearrange this equation, then this is equals to basically omega B omega D times TB TD over TA TC, right? And if I bring this WB to the other side, then basically I have WA omega C divided by omega B omega D. This is equals TB TD over TA TC. And since B and C, gear B and gear C are connected together, then we can say that omega B is equals to omega C. So we can cancel that. So omega B and omega C cancel out, and what we have is omega A over omega D equals to TB TD over TA TC. So omega A is input, omega B is output, and we can express omega with respect to n, right? So basically omega is equal to pi n over 60. So I can express omega with regards to n. So this is basically na over n d, and a is input, d is output, so this is equals to gear ratio. And if you look at this term, tb, td, ta, tc, if you look at tb, b, and td, both of them are output, right? So this is output. B is output of the AB system, and D is output of the CD system. So the top portion is actually output, right? And the bottom one is the sorry, this is not output, this is driven, and the bottom one is the driver. So sorry about that. So this is driven driver. So basically, from here we can say that the gear ratio for compounded gear can be calculated by product of driven teeth uh, over product of the driving teeth or driver teeth. So if you have a compound gear system, then you can actually calculate the gear ratio by simply calculating the product of the driven teeth over the product of the driving or driver teeth. Okay, let's look at the problem on the compound gear system, compound chain gear system. Calculate the gear ratio for the compound chain shown below. If the input gear rotates clockwise, in which direction does the output rotate? So it indicates that the input gear rotate clockwise. So this is clockwise, right? And we know that for train gear system, if the gear mesh with another gear, then the rotation will be the opposite of each other. Right? So with that, basically, if A rotate clockwise, then B will rotate counterclockwise, and B is connected to C. So C will also rotate clockwise, and C will drive D. So D will rotate counterclockwise, and D is connected to E, so E will rotate counterclockwise, clockwise direction. And E is connected to F, and since E is clockwise direction, F must be counterclockwise. So we know that the output gear, which is F, will rotate anti-clockwise, counterclockwise, right? The other question is with regards to the gear ratio. So gear ratio, from the derivation that we did earlier, the gear ratio is basically product of T for the driven gear, product of series. So gear ratio is equals to something wrong. Product of T So this is of a driven gear divided by product of T for the driver, right? So then we can just calculate the ratio between the two. And given here is basically the t value, and so this is equal. Let's look at the product of the t of the driver of the driven gear. So from here, you know that B is a driven, so is TB times uh, C is a driver, so D is driven, TD. E is a driver, F is driven, TF. Divided by the driver, which is TA, times TC times T E. Right? So basically, TB is equals to 100. TD is equals to TD is 100 times TF. TF is 100 divided by TA is 20. TC is 40. TC and finally TE is 10. Right? So basically I can cancel out. Right? And then 2 cancel out. I have 50 here. Right? 4 cancel out, become 5. Right? And then I cancel 2, this is 25. So this become 25 times 5, which is equals to 125. So it's similar to the answer here. So far we have looked at two type of gear system. One is the train gear system, and also the compound gear system. And the third gear system that we're going to look at is called planetary or epicyclic gear system. So the meaning of epicyclic gear system is one gear revolving upon another and around another. So the examples of epicyclic gear system is shown here in this figure. And the reason why this gear is being used is this gear can produce large gear ratio in a very small space. So for example, in the automotive application, then you need to have many gear ratios. For example, on the automatic gear automatic transmission system, then you're talking about minimum uh, four gear ratio, gear one until gear four, and then maybe you have one reverse gear. So in order to achieve those kind of gear ratios application in a very compact space, then epicyclic gear has been utilized quite widely. So let's look at the basic theory of epicyclic gear system. Usually, the epicyclic gear system, a very basic epicyclic system, will have this component. One is called planet. So planet will revolve around sun gear, and the planet gear is attached with an arm. to the center of sun gear. So as the planet gear revolves around the sun, then basically the tooth of the planet gear will measures with the sun planet gear. They revolve relative to each other. Uh, the basic gear theory for us to be able to calculate the gear ratios so on and so forth is so observe a point P, this point P, right? Gear B revolve once on its own axis as the arm rotates a full circle. So if the arm rotate full circle without any sun gear uh, meshes with the planet gear, so as the arm rotate full circle, then point P, right, will move around once, will rotate once, right? So it move 90 degrees, and then after that it move 180 degrees, and then it moves 100 and 270 degrees, and finally it returned back to its original position. So even though the gear, the planet gear P, the planet gear does not rotates relative to its axis, but since the arm rotate once, then basically the planet gear actually rotates once, right? So so if the arm stationary and gear C, which is the sun gear, rotates once, B will spin about its center by Tc over Tb, right? And again, Tc is number of tooth of a gear C, and Tb is a number of tooth uh, uh, on the gear B, the planet gear, right? So if C fixed, if C fixed, right, and the arm revolves once, then B will revolve Tc over Tb plus 1. The reason why you have a plus 1 is because of this reason, you know. So as it measures with as the tooth of gear B measures with the tooth of gear C, and as it revolves, then you get this rotation Tc over Tb. But when the arm revolve around the sun once, right? So you have this additional one revolutions due to the fact that, you know, even though planet gear does not measures with the sun gear, but the fact that it revolved once on the arm, the fact that the arm revolved once, planet gear actually revolve once. So that's why the if C is fixed, then arm revolve once, then B revolves by Tc over Tb plus 1 rotation. So that's basically the basic theory of epicyclic gear system, which will apply over and over again in subsequent lecture. So let's look at the application of this basic theory on a very simple system where you have a sun gear, arm, and a planet gear. So usually, then basically what you do is you have to name the individual gear, and for this particular case, sun gear is C, the planet gear is B, and the arm is A, right? And imagine that the whole system revolves once. So you just imagine, so whenever you want the first step in calculating the relative motions of all the gear system in the epicyclic gear is you have to imagine that the whole system revolves once. So you have to set up a table as such So step, action, this is the gear, right? And basically after that, then the step one is revolve all once. So you just imagine that all the planets, all the gear system in that particular epicyclic gear, revolve once. So basically A will revolve once, B will revolve once, C will revolve once. Second, identify gear that's fixed. So assume that for this particular gear system, in any gear system, there's always one gear that's fixed, that's not moving, right? So in this particular examples, we assume that C is fixed, so this is fixed, right? And since gear C is fixed, then we need to revolve it minus one, because C cannot revolve, so it should be minus one, so that the total is back to zero. So then what we do is we revolve C minus one. If you revolve C, which is the sun gear, minus one, right? And basically the gear B will revolve TC over TB, and TC is basically the number of teeth of gear C. TB is number of teeth of gear B. So the number of rotation of B will be TC over TB. And since B is not fixed connection, that doesn't have a fixed connection with C or B, where it revolves around its individual axis, then A will have zero rotation, right? Then the next step is you have to add them up together. Oh, by the way, you have to indicate the relative rotational movement or directions among all the gears. For example, C, just now we rotated minus one, right? So if C rotate clockwise, right, B will rotate uh, counterclockwise, right? So it's the opposite of the rotation of opposite of rotation of each other. So because of that, then if C rotate minus one, B will rotate TC over TB, and the direction is plus, because it's the opposite of C. If they are same directions, then basically both of them will be minus, right? So again, next is the third step is add them up together. So if 1 plus 0 is equals to 1, and 1 plus TC over TB is equals to 1 plus TC over TB, and 1 plus minus 1 equals to 0. So these are the relative movement of all these what do you call it, gears is in this particular epicyclic gear system. So it shows that if A, which is the arm, rotates once, then B will rotate 1 plus TC over TB. And the directions of the rotation would be the same between the arm and B, because both of them are plus value, right? So that's how you set up and analyze the relative motion, the relative movement between all the gears and also arm inside the epicyclic gear system. Let's look at these particular examples on a simple epicyclic gear. So a simple epicyclic gear has a fixed sun gear with 100 teeth. So this is the sun gear. It's called C. So TC is equals to 100. And a planet gear with a 50 teeth. So the planet gear is a TB, which has 50 teeth. Right? if arm is revolved once, how many times does the planet gear revolve? So basically, first, so there's a worked out solutions here, but let's go through step by step. So make a table. So make a table first. So okay, so basically the first one is this is a step, and then this is A, B, and C. So this is the sun gear. So this is fixed, right? And B is a planet gear, and A is the arm, right? So first step, as we discussed just now, step one, revolve all one. So A, B, and C revolve for one, and then you find the fixed gear, which is the sun gear, right? So revolve C minus one. So C, since C is fixed, then we revolve it minus one, and C measures with planet gear B, right? So because of that, then if C revolve minus one, B will revolve TC over TB, and the value of TC over TB is the directions of the rotations of the TC over TB, of the direction of the rotations of TB of gear B, which is the planet gear, will be the opposite of gear C, which is the sun gear. So because of that, since C is minus, B must be plus, and A, no rotation, right? So C rotate, but it just revolve around its axis. So A, the arm, does not revolve, so it's zero. Then we add all together. Okay? So in this particular case, I have not counted TC over TB yet. So let me just erase this. So if I calculate this, then this is TC, so this is a plus. TC is equals to 100, TB is 50, right? So this is plus 2, right? So if I add them together, so third step is add all. So this become 1 plus 0 is 1. So 1 plus 2 is 3. 1 minus 1 is equals to 0. So the question is, if arm revolve once, how many times does the planet gear revolve? So if the arm revolve once, the planet gear will revolve 3 times, right? So with this, then basically you can calculate. So if you know that the speed of A is 1 revolution per minute, the speed of B will be 3 revolution per minute. Right? So you can make that assumptions, and you can solve those kind of problem, right? And the directions of rotation of A is same as direction of rotation of B. So if A is clockwise, then B is also clockwise, right? So let's look at the application of the basic theory of epicyclic gear on this particular case. And in this particular case, call it case one, uh, the situation is as such, where you have arm is an input and D is the output. So if you look at this particular schematic, right? So what we have is we have the sun gear, right? And then this is the arm, and we have a planet gear, right? And for this particular case, is arm is the input, so this is the input, and D is the output, and D for this particular case is this is sun gear, so this is D. Yes. So this is sun gear, right? Um, uh, and C is fixed. So there's another gear that's shown here. So C is fixed. So this is outer casing of the gearbox. So usually on the out on the gear you have a gearbox. So this is C is the outer casing of the gearbox, and you have internal gear, internal teeth uh, for that particular gearbox, right? So internal teeth around it. So C is fixed. Hmm. Note that the planet and the internal gear rotate in the same direction. So if you have if we when we look at a gear system just now, and we talk about the sun at the center and the planet gear, right? So so if the sun rotate clockwise, and the planet gear that measures with to the sun gear will rotate the opposite direction, right? So if this is clockwise, then this will rotate counterclockwise, right? But if you have a internal gear measures with the external gear, so you have you have this is internal gear system. So you have internal gear of the casing. So this is equivalent to C just now, right? And this is the planet gear, and this is B, right? So as the planet gear move clockwise, so will the C, which is the internal gear, the gearbox, right? Because this is a meshing between the internal gear. So, so this is the opposite of what we discussed just now. Okay, so you have to remember that when we look at the directions of the rotations among all the gears, then you have to remember these rules. Okay, so let's look at the examples of problem of the case that we discussed just now, the case one, where the sun gear will be the output, A, the arm will be the input, and C will be fixed. So an epicyclic gear system, epicyclic gearbox has a fixed outer gear C, so C is fixed, right? So I can denote that as fixed, right? And TC is equals to 240, right? And the planet gear, so the planet gear is B, so TB is equals to 20, and the input is the arm or the cage A, and the output is the sun gear. So A input, and D, which is sun gear, is the output, right? So the question is, calculate the number of teeth on the sun gear and the ratio of the gearbox. So you need to we need to calculate the number of teeth on the sun gear because it's not given, and the gear ratio of the gearbox. So let's solve the first one first with regards to the teeth of the sun gear. So sun gear. So what we want to find is T D. Right? So if I sketch this, resketch this, so basically what I have is this. So this is the we call it C, right? And then we have a planet gear, two planet gear, right? So this is B, this is also B, and we have a sun gear. So sun gear is called D, right? So if I want to find diameter of C, right? So it's equals to diameter of B plus diameter of D plus diameter of B. So it's equals to 2 diameter of B plus diameter of D, right? So I can say that, so I just put in terms of D. Diameter of C is equals to 2 diameter of B plus diameter of D. And we want to find diameter, we want to find TD. So if you remember, we have defined modules is equals to Tx over dx, right? So module for the gear that mesh together, they are the same. So I can see that module for module for A, module for B is equals to module for C equals to module for D. And so I can do this. So dx equals to dx over m, right? Based on this. So MB, MC, MD are the same. So I just call it M. So if that's the case, so if I say this is 1, this is 2, and this would say this is 2. So 1 into 2. What I have is I have dc over m is equals to 2 dp over m plus dt over m. And I can cancel m out, right? So I left with this equation, and td is equals to tc minus 2 dp, right? And this is equals to tc is equals to 240 minus 2 dB is 20. So this is equals to 200. So we have calculated what is TD based on this association. So remember that, if you want to find TD is the diameter is proportional to the number of teeth for a particular gear that are measured together. So next is we want to find the gear ratio. So gear ratio is basically the speed of the input over output. So basically NA over N, and the output is ND. Right? So the way to do that, basically we have to apply the basic epicyclic gear theory. Let me erase all this. Okay, so to apply that theory, basically we make a box. So it should have 3 rows. 1, 2, 3. Because you have 3 steps that we need to perform. Uh, So the first one is basically uh, step. And then we have one, two, okay. So steps, and then we have the gear. So we have the arm A, and then we have B, C, and D gear. And I know that D is the output, so this is output, and the input is A, so this is input, and C is fixed, so C is fixed. So first step, as we did before, revolve all by one. So A is 1, B is 1, C is 1, and D is 1. Then we identify the fixed gear. The fixed gear is C. So we need to revolve C minus 1. So C will be minus 1. And if you look at C, right, C is attached, is meshes with B, right? So if C rotate once minus 1, right, B will rotate TC over TB, right? Number of gear C over number of gear B. And the direction should be similar direction because this is internal gear. So as B rotate, let's say for example, uh, clockwise, so will the gear C will rotate clockwise because this is internal gear. So because of that, the signage here is also minus, similar signage of C. And the value is basically minus TC is equals to TC is equals to 240 divided by TB is equals to 20. So I'm going to erase this. So that is basically minus 12. Right? So basically that is the B. And if you look at B, B measures to D. B measures with gear D, right? So then the number of rotations of D would be T. So the driver is B, dB over dC. And the direction is opposite of direction of B. So since B is minus, this must be plus. Right? So this indicates that, so this is one rotation of B over one rotation of C. But B does not rotate once. It rotates 12 times. So because of that, this times 12. Right? So this is equals to plus TB is equals to 20. TC is equals to 200 and I'm sorry. So this is TB over TD, right? So B measures to D. Again, rotation is the same. It's just that TD. So TD is equals to 200, right? Times 12. So this is plus. So cancel out. So this is 1 over 10. So this is 1.2. So basically, if a B rotates minus 12 times, minus its directions, D will rotate 1.2 times only. Okay. And what happened to A? A does not move, right? Because it's independent of all the gears, right? So it's equals to 0. Right? So the next step we add all together. So when we add them up, so this become 1, this become minus 11, this become 0, and this is 2.2. So we need to calculate the gear ratio just now. So gear ratio is equals to number of rotations of input, which is n, a input, over output is equals to n, b. And so this is every one rotation of the arm will rotate 2.2 times of gear D. So that's the gear ratio. So for this particular case, the one that you have to watch out is this. You have to remember this. Right? So basically, so as B rotates, right, it will measure the with a D. So the TB over TC actually define one rotation of B per per rotation of D. So how many how much D will rotate based on one rotation of a B. But again, as mentioned just now, B does not rotate once, but it rotates 12 times. So that's why you have 2 times 12. Okay. Okay, let's look at the problem for case 2. Again, the application of the basic theory of epicyclic gear on case 2, where in case 2, the sun gear D is fixed and the internal gear C is an output. So it's a bit different compared to case 1 that we did just now. In case 1, C, what do you call the internal gear C, which is the casing of the gearbox, is fixed, and D is the output. So for this particular examples, the sun gear D is fixed. So the sun gear D is fixed, and the internal gear C is the output. So internal gear is actually connected to a shaft, and this is going to be the output, and the arm is the input. So let's look at the examples problem of the case 2, where the internal gear C, the outer gear C, is the output, and the sun gear is fixed. Right? So an epicyclic gear box has a fixed sun gear D. So sun gear is D, and the internal gear C is the output with the 300 teeth. So it's given that TC is equals to 300, and the planet gear, so planet gear is B, so TB is equals to 30, and the input is the arm gear C. Calculate number of teeth of the sun gear. So basically we want to know what is a TD, and the ratio of the gearbox. So we want to know what is N A over N C. So those are things that we need to find out, right? So if I resketch this particular gear system, basically I have the output, the outside, the outer gear is we call it C, and we have 2 planet gear inside, and we have a sun gear at the center, right? And planet gear is called B, and the sun gear is called D, and the arm is called A. That's A, right? And gear and the C is the output, and the input is A, and D is fixed. So let's look at the first question, where TD is. Again, we can use the relationship with the diameter and number of teeth for a gear system. So we can say that diameter of C is equals to 2 diameter of B plus diameter, I'm sorry, so this is C. That's correct. Plus the diameter of D. Right? So then I can replace this with a TC is equals to 2 TB plus TD. We want to find D, so TD is simply TC minus 2TB. So TC is equals to 300 and TB is equals to 30. So this is equals to 240. So I know that TD is 240. Okay, to solve for the gear ratio equals to NA over NC, then basically we need to apply the gear ratio, make a table as we did earlier in the previous example. So let me just erase this. So I'm going to make a table. So we have one line there. And then we have okay. So I have A, B, C, and D. Right. So step again. The first step is revolve all by one. So this is one, 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 one. Before that, let me just put it here. This is input. Output is C. So this is output, and D is fixed. Right? D is fixed. Okay, so first we revolve all at once. Next is we identify the fixed gear, which is D. So revolve D minus 1. So D will become minus 1. Right? So D is attached to, is meshes with B. Right? So every time one rotation of D will result in rotation of B by how much? By T D, which is driver, over T B. And basically in terms of the orientation, so since this is external gear that's meshes with each other, so basically if D clockwise, C is the opposite. So since D is minus 1, then B should be plus. Okay, so let's plug in the number. TD is equals to 240 divided by TB is equals to 30. So this is plus 8. Right? So B, and then we next B measures with C, right? So every one revolutions of the B, right, it'll make TB over TC revolution, right? But it does not make one revolution, but it makes actually 8 revolution. B revolve 8 times. So every one revolutions of D, 8 will revolve 8 times. And every revolutions of B, C will make TB over TC, but it's not only one revolution of B, but it's 8. So I times 8, right? In terms of direction, so since this is internal gear between B and C, meshing between B and C is internal gear. So it should be the same directions of B. So because of that, this since B is plus, this is also plus. Right? So if I plug in the number, then basically this is plus 8. TB is equals to 30 and TC is equals to 300. Right? So then basically this is plus 0.8. So then the third step is again add all. So again, A is 0. So A does not rotate because it's independent. So then you add them up together, we have 1. 1 plus 8 is equals to 9. And then this is 1.8. And 1 plus minus 1 is equals to 0. So then we can calculate the gear ratio, which is number of rotation of A over C is equals to 1 over 1.8. So that's the gear ratio. So every 1 rotations of A, it'll make 9 rotations of B and make 1 rotation of 1.8 rotation of gear C, and they are all in the same direction, right? So if A is 1 rpm, B will be 9 rpm, C will be 1.8 rpm. If A is 2 rpm, right? If A is equals to 2, then basically and B will equals to 2 times 9 equals to 18, right? And B and C is equal to 1.8 times 2, which is 3.6 rpm, right? Okay, so the third case of epicyclic gear problem is as such, where we have a compound gear C and D is introduced. So just now what we have is basically we have a series of gear systems connected together. Now we have a compound gear. So compound gear C and D is introduced for this particular example. So C and D. Gear B is fixed. So B is fixed, and gear C rotates upon it and around it. So gear C is rotates around it and upon it. And gear C are rigidly attached to gear D. So C and D are connected. So C and D are connected with the same shaft. And whatever speed of C is the same speed of D. And gear D mesh with the output gear E. So E become the output gear E. So there's a shaft connected to gear E as an output. Right? So we want to look at these particular examples and see how we can solve such problem. Okay, so let's look at the examples of problem related to compounded gear on the epicyclic system. Um, so it's given here that the epicyclic gear shows here with gear TC is 100 teeth, and TB is equals to 50, and TD is equals to 100, and TE is equals to 100, right? So we are asked to calculate the gear ratio, and gear ratio is basically the output, the input. So basically an A is the input, and and okay. So in order for us to solve this, then we do the same thing as before, right? So so again, we make a table, and basically okay. So basically we have gear A, so B, C, D, and E. So it stays here, identify that gear B is fixed. So B is fixed. This is fixed. A is the input, and E is the output. Right? So what we did is what we want to do is this. So first, what we do is again as before, revolve all one. So all revolve once. Second, we find what's the fixed gear. So fixed gear is B. So revolve B minus 1. So B is minus 1. So if you look at B, B is connected to C. One revolution at B is equals to, so one revolution of B is equals to TB over TC. And the direction is the opposite because this is external gear. So since B is minus, C will be plus. And if you plug in the number, TB is equals to 50, TC is equals to 100. So this is plus 1 over 2. So one rotation of B equals to, will rotate C half a rotation. Yeah? And so next we want to look at what happened next. So we look at B, okay? And B is attached to C, and C is attached to D, right? So whatever number of rotation of C is equals to number of rotation of D. So actually we can combine them. So C, D, and can be combined in one column, right? So the number of rotation and also the direction of the rotate will be the same between C and D because they are in the on the they are attached with a fixed shaft, right? So then I can just erase this and erase this, and this will be E out, right? So C and D are connected together, and D is connected to E, right? So one rotational of D equals to how many rotation of E? So so D meshes with E. So every rotation of D will result in TD over T of rotation, right? And the directions of the rotation is opposite because it's external gear, so that meshes together. So this will be minus because C and D is plus. So so this is based on the assumptions that TD rotate once, but TD does not rotate once, right? So D does not rotate once. D only rotate half. So you have to times half over here. So times 1 over 2, right? So then if I plug in the number, so TD is 50. So TD is 50. Sorry. So TD is D has 50. So this is 50. So this is minus TD is equals to 50. TE is equals to 100 times 1 over 2. And this is equals to minus 1 over 4. Okay. So what happened to A? A again is independent of each of all the gears, so is no rotations there. So if we next step is basically add them together, add all. So this become 1. 1 minus 1 equals to 0. This is 1.5, and 1 minus plus 1 minus 1.4, 1 over 4. So this is 3 over 4. So the rotation. So this is the result of all rotation after it's being added up. So it shows that if A revolve once, B zero, C and D will revolve 1.5 times, right? Same direction of A. And E will also revolve in the same directions of A, but only three-quarter of a turns only, right? So then we can calculate our gear ratio is equals to NA is equals to 1, and E is equals to 3 over 4. Right? So this is equal to 4 over